Professor Belden. This is Trigonometry, Chapter 1, Section 2, Radian Applications. This is Part 3 of the video, and this will be on the combinations of the velocities and speeds, so the linear and the angular speeds. So let's first off talk about the general rule. So I have person 1 and person 2. They're holding hands and they're walking around a circle here, and they walk together from a pivotal point. They walk the same angle over the same amount of time. So let's think about what happens here. So I have person 1 and person 2. Okay, well, angular velocity is the angle over time. Well, both people turn the same angle and they walked hand in hand over the same amount of time. And therefore, in this case, they have the same angular velocities. Okay. However, let's look at the linear speeds, right? V equals the distance they traveled over time for person 1 and person 2. Well, the distance traveled for person 2 is clearly much longer than the distance traveled for person 1. Person 2 had to walk longer. They walked the same amount of time, but person 2 had to walk longer. So therefore, person 2 has more distance over the same amount of time. Therefore, in this case, the velocities are not equal. In fact, the velocity for person 2 is more, and they had to travel faster. So think of it as a race car track, the outer track, the person has to drive faster. Or if you had a track and field, the person in the outer track has to run faster. Okay, so that is the general idea of angular and linear speed and velocity in terms of a circle. And basically, the farther you are out, the farther you go, the angular speed will always be the same. You turn the same angle, same amount of time. However, the linear speed will increase because you have to go faster. Okay, let's look at the next one. So both of these projectors are missing a lens, and that's irrelevant here. What we're talking about is which one is mechanically correct, which one will actually show a movie correctly based on how it feeds. To take a second to think about it and decide for yourself first. Okay, so projector A is in fact the one that's incorrect because it feeds from the reel itself to the other reel. And as a result, this reel keeps a constant RPM, but the film itself is changing radius. So as a result, the RPMs, or angular velocity, will stay the same, but the linear velocity is going to continually change with the radius of the film. Therefore, the rate at which it shows will change, so the video will appear to be faster and slower at parts depending on the radius of that film. However, the second one is mechanically correct, which is the reason for the box in the first place, is it feeds from the inside. And as a result, those little gears in the inside maintain a constant radius. As a result, because they have the same RPM constantly and the same radius constantly, they have the same linear and angular velocity. Therefore, the film that's feeding through it will always feed the same speed, and your film will maintain a nice 30 frames per second, or whatever it happens to be. Okay, let's try some formulas here. So we know the concept of how angular and linear velocity relate. Now we want to know the formula. So velocity, speed, linear, and angular velocity are related by radius. Okay, so it's a multiple of r. So these are our formulas we had before. If you put them together, you can get the new formula for velocity. Okay, so I have an 8-inch diameter gear that turns at 60 RPMs, and I want to know the RPMs of the 24-inch diameter gear if they're connected. Okay, all right. So the 24-inch diameter would actually be a 12-inch radius, and the 8-inch diameter would actually be a 4-inch radius. Okay, so let's start with what we know. This is spinning at the center at 60 RPM. And again, we can't use RPM because that doesn't help us. So 60 revolutions to 1 minute. So we'll convert that to radians. So 1 revolution is 2 pi radians. So that gives me 120 pi radians to the minute. So that is my proper angular velocity. That is the angular velocity. We'll call this the smaller one. So I'll put a little s in there. So this will be my larger one. That'll be my smaller one. Okay? Because they'll have different numbers here. Okay. So now I want to know on the outer edge, how fast am these gears traveling on the outer edge? Well, using my new formula, the velocity of the smaller gear is the radius of the smaller gear times the angular velocity of the smaller gear. Alright, well the radius of that smaller gear is 4 inches. And the angular velocity we just calculated, which is 120 pi and to 1 minute. We don't need to put the radians in there. So that gives me 480 pi inches per minute. So that is in fact the velocity of the smaller gear, how fast it's turning. Okay, so that velocity right there is the 480 pi. However, these are connected. One can't spin faster than the other, so they have to be spinning at the same speed. So in fact, these are both the same, the large and the small. They're the same velocity, so we can stick the old VL on there also. Okay, so now we want to know how much that's spinning in the center there. That's the angular velocity, right? So take the same formula again. The velocity of the larger gear is the radius of the larger gear times the angular. Oops, that's wrong. That's the multiply, right? So multiply times the angular of the larger one. Okay, well we just calculated the larger one. That's 480 pi inches per minute. The radius of the larger one is 12 inches. And we're trying to calculate the center of the larger one for the angular. That's 12. So we'll divide by our 12 inches. So that'll cancel over here. It'll cancel the inches here, leave me minutes. So now I'm down to a radian measure on top as a result. So that gives me, let's see, 40 divided by 12 would be a 40, correct? So let's see, the angle of this one would be 40. Let's see, the pi would still be there. And that's radians per minute. Okay, we'll circle that. So this center right here is spinning at 40 pi radians per minute. So the last thing we want to know is the RPMs of that center, how much it's spinning. That's just converting that. So we'll multiply this by the 1 revolution to 2 pi radians. So we can cancel the radians and the pi there. So that'll cancel the radians and the pi, leaving me with 20 revolutions to 1 minute. Right? Because the radians will cancel, the pi's will cancel. 20 over 2 is 20. I'm sorry, 40 over 2 is 20. So that's 20 RPMs is our final answer. Okay, so pause the video and try the student problem. Looking at this problem, of course, to see that there are two different angular velocities, speeds, and two different linear speeds. In some cases, they could be the same. So in this case, the linear velocities are the same, but the angles are different because the bigger gear had to work less to spin that number of times. Okay, the next example in the grinding stone. The grinding stone is being moved by a water wheel, probably into some kind of river or stream, and that's moving at 4 miles per hour. And that's a velocity. We'll call that the W for there. And we'll call this one G for this. So this one moves here, right? It'll move the same way, and that'll be the we need the velocity of the grinding stone there. Okay, and they both have angular velocities in the center, which we don't know yet. All we know is the water wheel is 12 feet, so that's going to be a 6-foot radius. And the grinding stone is 3 feet. That's a big stone, so that's going to be 1.5 feet in radius there. Okay, so we'll do the water wheel over on the left side here. Water wheel. And we will do the grinding stone over here on the right. So the first off, we have a little problem here, is it's 4 miles per hour. That 4 miles per hour has a couple problems. Because if we're going to be doing RPMs, can't use hours, need minutes. And the other thing is we have miles, but the radius here is in feet. So we can't either have both miles or both feet. Feet is probably going to be better since most of things are in feet here. So we'll do the feet first. So that's 1 mile is 5,280 feet. And we also need to convert the hour. So 1 hour is 60 minutes. Okay, so we multiply through and we cancel. So that's going to cancel the hours. That's going to cancel the miles, leaving me with feet per minute. So that's going to be 352 feet per minute. And that is the speed of the water wheel, so VW. So that's 352 feet per minute. There's another way to put 4 miles per hour, which is going to work better for us. So now we can put that in the formula. Because the V for the water wheel and the radius of the water wheel times the angular velocity of the water wheel. So we calculated this as 352 feet per minute. And the radius we knew was 6 feet. And we want to know how fast it's spinning for the angle. So we'll divide by the 6 feet. So I'm going to move this over to here. So my angular velocity of the water wheel, okay, so 352 over 6 is not going to go in evenly. So I'm going to keep the fraction though. So that'll be 176 over 3 radians per minute over minutes. Okay. We want to notice here, that's the water wheel center. So the center of that wheel is spinning at that many radians per minute. But they're connected with a rod. They're connected. So if the big wheel spins 100 times, the small wheel has to spin 100 times. If the small wheel spins 2 times, the big wheel spins 2 times. So that means they spin the same amount of times. So that means they have the same angular velocity. They're the same. There's no difference. Okay? So the last piece now is getting the speed linearly of the grinding wheel. So we'll put that over here. So the velocity of the grinding wheel is the radius of the grinding wheel times the angular velocity of the grinding wheel. Well, we know the radius, that's 1.5 feet. And we know that the angular velocities are the same for both, which is 176 over 3. And again, we're just going to keep the minutes on there. So the velocity of the grinding stone is going to be feet per minute. And that gives me a final calculation of 88 feet per minute. So that is how fast the outer edge of this is spinning. So that's 88 feet per minute. All right, so we have 2 different linear speeds, but they have the same angular speed here in the middle. So it's a reverse problem we had before. So the last thing is, what is the RPMs they're both standing? Since they both have the same angular speed, they're both the same RPMs. So I take my 176 radians to minutes and multiply that by 2 pi radians to 1 revolution. So the radians will cancel. So that's 176, which is divisible by 2. So that'll give me 88 over 3. So that's 88 over 3 pi revolutions to minutes. So that is your RPMs for your final answer. And that is the end of part 3.